So hello everyone, this is Shammi and currently I'm a PhD scholar working in the field of partial differential equations in Department of Mathematics, IIT Delhi. So let us start the week 3 session. So in the week 3, what we have studied in the lectures, we basically started with the chain rule. And when studying the chain rule, what we did, we after studying the chain rule, we saw like how can we basically invert the chain rule to get the derivatives in another form. The basic idea being was using the Cramer's rule to invert the system equations we get after differentiating the functions. And then we saw some examples, and after that we studied what do we mean by a homogeneous function of degree n. And then we saw that there's Euler's theorem that gives directly the value of the function, basically some particular form of particular equation form for those functions, and basically if I want to state it explicitly, it says that the x times the del f by del x plus y times del f by del y equal to n times our function itself if the function is homogeneous of degree n. And then we saw other type of things which we can directly compute if our function is homogeneous. And then we moved on to thing, basically we parameterize our curves, and we eventually saw that if you have a surface, so that surface, the level surface, the gradient turns out to be normal to the level surface at the points. And then with help of that, we actually able to write the equations of the tangent plane of the surface at a point, and also the normal line which is passing at a point of the surface. Then moving onwards, we saw that after calculating these tangent plane values and on these normal lines, we worked on the to calculate the extreme values of the functions of more than one variable. And for that, we with help of the Taylor polynomial, we form some tests. We form some tests. The main one was for the two-dimensional case. We have the second derivative test, which we have formed with the help of Taylor polynomial. And eventually we get some criteria. If the function satisfies those criteria, this will actually give us basically when our function will have local maxima, minima, or it will have a saddle point or a saddle point. So well, we studied the secondary test is not always helpful. Well, it's not always works because it works on a particular values over something which we value, which is called discriminant. And with that, we actually conclude our week 3. So, like without further ado, let's start the problems based on these topics. So let us start first with the homogeneous questions which we have studied. So let me write the first question of this session. So first question is, I want to, if my function is x raised to power 5 plus y raised to power 5 whole divided by x square plus y square, then x square fxx plus 2xy fxy plus y square fyy equals. Now, as we can see that basically if we try to compute the partial derivatives directly, it will be very tough for us because you have to calculate the second partial derivative of this function, and this is not just an ordinary function, it's a rational function, and to evaluate this derivative we have to employ the product rule, and that is very cumbersome. So but we can we can observe one thing: the function given to us is a homogeneous function. So let us see, is it actually let us prove it is homogeneous, and see what's the degree of this function, what is the homogeneous degree of this function. And once we have that, we saw in the theory that this expression can be directly evaluated with the formulas which we have derived in the theory. So let us see what a degree of homogeneity it possesses. So to check the homogeneity, what we will do, we will just plug in variables lambda x and lambda y and instead of x and y. So let us plug f at lambda x, lambda y. This will be lambda x raised to the power of 5 and lambda y raised to the power of 5 all divided by lambda x square, lambda square, and again lambda square y square. This is nothing but lambda raised to the power of 5 x raised to the power of 5 plus y raised to the power of 5 lambda square x square plus y square, and this is nothing but just lambda cube f of x comma y. So what this will imply? This is imply that f is a basically a homogeneous function of degree. F is genius of degree what? 3. Okay, so now for the homogeneous function, what we have said that this thing, this expression x square, sorry, fx6 plus 2xy fxy plus y square fyy. This is nothing but n times n minus 1 of a function. Now the given here is the degree is given to be 3. So this will be just nothing but 3 times 3 minus 1 f. So this will be nothing but 6 times f. So this will be our answer. So we can see with the formula we just directly evaluate this expression. But if we don't know the function is homogeneous, then it will be very cumbersome to evaluate this expression. Like it will be too lengthy. Okay, so let's proceed. So let's try one more question based on homogeneity. X y cube x square y square x4. Then x del f by del x plus y times del f by del y is. So we can evaluate this, but again, like even though it's easy to compute this in this case, this expression, but let us apply the Euler's theorem. Like again, also this is coming from Euler's theorem. So let us check its homogeneity of this function. So I put f lambda x lambda y. This will be lambda raised power x raised to power y cube x square y square plus x raised to power 4. So this is just, if you see, this is nothing but the lambda raised to power of 4 fxy only. So this is then f is then f is homogeneous of degree what? Degree 4. Then we know from the Euler's theorem that del f by del x, or x times del f plus del f by del x, y times del f by del y is nothing but given as n times f, where n is my the homogeneous degree of my function, and here the degree is 4. So this expression is directly can be evaluated, and this is nothing but 4 times our function. And we would like to check the Euler's equation, so let us check by computing exactly how it turns out. So let us see. A function was given as this xy cube plus x square y square plus x raised to power 4. Our function is x y cube x square y square plus x raised to power of 4. So so let us evaluate directly this expression. So del f by del x would be, so we know how to partially differentiate these things. So to get the partial derivative, I will treat the other function, other variables as constants, and just directly differentiate as we do in one dimension. So this would be y cube 2x y square plus 4x cube, and likewise del f by del y would be 3x y square 2x square y, and let us see, right, x del f by del x plus y del f by del y. So this would be x y cube twice of x square y square plus 4 times x to the power of 4, and likewise here this would be 3x y cube plus 2x square y square. So if I add these things, so I will get 4 times x y cube plus 4 times x square y square plus 4 times x to the power of 4, and this is nothing but 4 times our function only, which we have shown directly with the help of the Euler's theorem. So we see that's a really powerful theorem we have, because we don't have to do all these computations, even though computations are look very not so hard in this case. But if we have some function which is not so easy differentiable, partially differentiable, then Euler's theorem comes very handy. Okay, let's proceed. So now so we saw how to basically calculate the Jacobians in higher dimension. Basically calculate Jacobians. So Jacobians are nothing but sort of we can say sort of similar extension of partial derivatives to higher dimensions in some sense, in very loosely sense, not exactly. So let's have one question on based on computing the Jacobians. So if my function x is given as 2u minus 3v and y given as u plus v. Then I need to compute del x y whole divided by del of u v. Okay, so we have to compute this. So one of the methods to remember what exactly is this expression is. So what can I do? I just this is a we can say it is a determinant which I have to evaluate, or how I evaluate determinant. This will be 2 cross 2 determinant, and I have, since in the denominator I have differentiating with respect to u and v, so I have to take partial derivatives with respect to u and v only, and here the functions we differentiate are x and y only. So, and how we write, so for this x and y, u and v. So this implies from the first row I have to differentiate the function x, and in the first column, first row and first column, since u is there, so I have to differentiate x with respect to u only. So here I will have del x by del u. Likewise, this will have del x by del v, and then we have del u by del y, and then we have del sorry, I just wrote something wrong here. So this will be del y by del u, del y by del v. Okay, and now we like to have to evaluate these derivatives. So let us evaluate these derivatives. So del x by del u, like we can, or also we can directly see. So del x by del u is have to differentiate these things. And so this will be 2 only, and I have differentiate with respect to v. This will be minus 3, and when I differentiate y with respect to u, this will be 1, and this will be 1 also. So this is nothing but 2 times minus of minus 3. So this is 5. So the value of this Jacobian is 5. And next, if you like to suppose in the given question, if we have given also these things, that also compute, let's say del uv whole divided by del x of x y. So, and to evaluate these type of expressions, we can see either we can do the same method, like we have to compute the determinant, or we can use one more, that identity, that these things have this property that del uv del xy times del xy whole divided by del uv, it is 1 only. So since I have computed this expression, this del x by del uv, so I know I can find the value of del uv by del xy. This will be 1 times 5, which we have evaluated earlier, or we can also see by definition that this actually turns out to be 1 by 5 only. So del uv del xy, this would be just evaluating the determinant of these things. That again we have u, v, and I have to differentiate with respect to x and y. So del u by del x, del u by del y, del v by del x, del v by del y. So now I know x is 2u minus 3v, and y is u plus v. So what we can see here is that we have to write this u and v in terms of x and y only. So let us see how can we represent u and v in terms of x and y only. So if I multiply this equation by 2 minus 2, so this gives me x minus 2y, equal to minus 3v minus 2v. So this is minus 5v, and this will imply that v is nothing but 1 by 5 of 2y minus x. And then u is given in form of y minus v, and y is minus v, and v is given as 1 by 5 times 2y minus x, y minus 2 by 5y plus x by 5. So this is nothing but x by 5 plus 3 by 5y, right? So now we just have to differentiate and plug in the values here. So let us u is nothing but x plus 5 and 3 by 5 times y. This is my u. And this is v. So I just have to plug in the values here. So del uv has to equal del xy So now, as we saw earlier, this is nothing but del u by del x, del u by del y, and this is del v by del x, del v by del y. So let us differentiate u with respect to x. So this would be 1 by 5. With respect to when we differentiate, this will be 3 by 5. And likewise, when I differentiate v with respect to x, this would be minus 1 by 5. And if I differentiate with respect to y, this will be 2 by 5. So if I evaluate this thing, this would be 2 by 25. This is just a determinant, and this is minus 3 by 25. So this one more minus here. So this is 5 by 25, and this turns out 1 by 5, which we have evaluated by the identity itself. 1 by 5, which was coming earlier. Here we can see. So the identity holds, and we are actually getting the expression that right away. So that's with that we can also compute the value of our these Jacobians. Okay, so now so now let us moving on. Now we would like to see that we saw that how to evaluate the tangent plane and the normal lines for our any level surface given to us, and we evaluate these quantities or these things in theory. So let us have some questions based on these concepts. So let us have some questions. So okay, so let us start. So what we have to evaluate. Let us see the equation of the tangent plane to the surface x square minus x square plus 2xy minus y square plus z square equal to 7 at point 1 minus 1 3 is alpha x plus beta y plus gamma z equal to 14. Then find the value of alpha plus beta plus gamma. Okay, so we have to find the value of alpha plus beta plus gamma. So to find the value of alpha beta plus gamma, we just have to find the equation of the tangent plane. So to find the equation of the tangent plane, as we saw in our theory, that with the help of gradient we evaluate the tangent plane, and so the tangent plane at point the tangent plane to the surface fx yz equal to c at, let's say, point x naught y naught z naught is, so this is given as the partial derivative of x is with respect to x at the point x naught y naught z naught times x minus x naught plus similarly fy at x naught y naught z naught times y minus y naught plus fz f naught y naught z naught at z minus z naught equal to 0. So this is the equation of the tangent plane passing at the point x naught y naught z naught. So to calculate this, we have to just here the function given is, here we have is given as x square plus 2xy minus y square plus z square. This is our function. So let us evaluate the partial derivatives. So fx would be 2x plus 2y. Fy would be minus 2y. So this we have actually, so this will be 2 of x minus 2 of y, and partial derivative with respect to z is given as 2z. So now I have to evaluate these values at point. The point is 1 minus and 3. So this is at 1 and minus and 3 I have to evaluate. So if I evaluate this will be 2 minus 2, so this is 0. Fy would be 4 and fz would be 6. So the equation of the tangent plane is zero times x minus 1 fy times y minus 1, and then 6 times z minus, the point is 3, equal, this will be equal to 0. So when I evaluate, this is 4y plus 4, 6z minus 18 equal to 0. Then this is 4y plus 6z equal to 14. And this is the sort of the same expression we have here. This alpha plus beta plus gamma, alpha x plus beta y plus gamma is equal to 14. So what this will imply? This will imply the alpha is my 0, my beta is 4, and my gamma is what? This is 6. So this is by comparing the equation we have here. So then the value of alpha plus beta plus gamma is nothing but 10. Okay, so that's how you basically do this question. So you have to evaluate the equation of the tangent plane. You have to, what you have to do, you have to just find a partial derivatives, and then you know the how to evaluate, how you know the equation of tangent plane in general. So you have just to plug in the value. That's all you have to do. Okay, so let's move on, and let's find one. Let's put one more question. Let us evaluate how can we evaluate the normal line at a point. So the parametric equation of the normal line to the surface, the surface is x cube minus xyz equal to 7 2 at point, let's say p 4 2 minus 1 is so again, as you have seen in the theory, to evaluate the equation of the normal line, we know that is given as equation of normal at, let's say, point is given as x naught, y naught, z naught is, so this is given as x equal to x naught plus fx of x naught, y naught, z naught times t. Then y will be equal to y naught plus fy, x naught, y naught, z naught times t, and likewise z is z naught plus fz, f naught, y naught, z naught times t. So that's the equation of a normal at a point. This. So again, to find the equation of the normal line, again we have to calculate the partial derivatives of our function. So here the function given as fxyz is nothing but x cube minus xyz. So fx is 3x square minus yz, fy is minus xz, and fz is what? Minus xy. Then I have to, then at point, the point we have here, then at point p is equal to what? The point we had is 4 2 minus 1. fx is given as 3 times 16 minus 2. So this will be 50. Fy at p would be minus x times z. So this is minus 4 times minus 1. So this is 4. Then fz at p is equal to minus 4 times 2. So this will be minus 8. So the equation is so I have to plug in the value. So this will be x equal to 4 plus 50t. Y would be equal to 4 plus, so the point is 2. So this would be 2 plus 40, and z would be equal to minus 1 plus, so minus 80 basically, where I'm varying t from real numbers. So this is my equation of the normal line at this point. So I think it's again very easy to compute. You just have to plug in the values. You have to evaluate the partial derivatives, and then after evaluating the partial derivatives, you just have to plug in the value, and after that you will be able to evaluate the equation of the normal line. So I hope it's clear. So let us proceed, and so let us now discuss some questions based on the calculating the basically maximum minimum points for more than one variable functions. So basically we would like to use the second derivative test which we have studied in our theory. So let's start with that. So till now we have done 5 questions. So for the 6th question, for function fxy equal to x square plus y square minus mxy plus 4, a point 0 0 is a saddle point if so you have to find the values of m so that this function has a saddle point at the point 0 0. Okay, so we know that for the second derivative test we do know that for the exact values for which we are getting the saddle point, basically at least an idea. So so let us have, we have 4 options. We have to see which option satisfies the criteria. Like we are absolutely sure that the function will have saddle point there, m equal to -1, m equal to 0, m equal to 1, and then we have m equal to 3. So let us compute the value of the determinant which is in the second derivative test. So for that we need to calculate the second order partial derivatives. So the fx given as 2x minus my, the fy would be 2y minus mx. So then if fxx would be twice of 2 only. And fyy would be again 2 only, and then fxy, this will be minus m. Now we need know that the for saddle point, one thing we could have is we may have d which is equal to fxx fyy minus fxy whole square. This thing has to be less than equal to 0. So less than 0. So what is this d now? D is 2 times 2 minus m square. So this is nothing but 4 times 4 minus m square, and I want this has to be less than 0. So at least to have a guarantee that the point we're considering is a saddle point. So let us plug for the values which we have. We have m to be -1 0 1 and 3. -1 0 1 and 3. And then we have to see what is the value of d. So this would be 3. This is 4. This is again 4 minus 1. This is 3 again. This is 3, and again we have 4 minus m square. So 4 minus 9 would be -5. And I want this to be negative, and to have this thing to be negative, what do we have? And since we need this expression to be negative, so let us write this thing. This is so this thing which we are getting here is, in this case only we are getting this to be negative. So for the value of m equal to 3, we have a saddle point. Basically, we have 0, 0 as saddle point. So let me write clearly. We have 0, 0 as saddle point. Okay, so for m equal to 3, in other cases, we don't have this value to be negative. We have things to be positive. So either we are getting a local maxima, local minimum, but certainly we're not getting a saddle point there. So that's how basically you can evaluate this. You can use this. This is coming from the second derivative test. So let's have one more question based on these things, based on the second derivative test. So let f be a function from R2 to R, given as fxy equal to x cube minus 12x plus y cube minus 75y plus 91. Then the point 2, 5 is we have to see whether this is a point of local maxima, minima, or a saddle point. So let us check. So to check, we have to calculate the second order partial derivative. So let us evaluate the second order partial derivatives. So we have fx equal to 3x square minus 12, fy given as 3y square minus 75. Then we have fxx given as 6x and fyy given as 6y. fxy then given as 0 only. And then again, you have to evaluate this value at 0.25. So at point we have fx6 at 2, 5 is given as 12, fyy given as 30, and fxy is at any point is 0 only. So then d is given as fx6 fyy minus fxy square. So this would be 12 times 30 minus 0. So this is something in an expression which is 360, which is positive. So this is a point where either we have a local maxima or minima depending on the value of fxx. So let's check. But we have given as fxx is 12, which is positive. So this implies by second derivative test, we have by second we have the point given to, we have the point p is equal to 5 is a point of local minima, because our value of this partial derivative with respect to x, the second partial derivative with respect to x is positive, so this will be a point of minima only. And I guess I hope this will be clear. So let us come back to another one more question of homogeneous things, the Euler theorem which we did. So let us start with that question. So let u given as log of x cube plus y cube whole divided by x square plus y square, then the value of x times del u by del x plus y times del u by del y is so here we can say the given function given to us not homogeneous, but the expression inside the logarithmic thing, this looks like an expression which could be homogeneous. So and for homogeneous function, we know that this expression can the expression which we like to find out, this expression can be directly computed and by the Euler's theorem. So what we can do, we to solve this, what we do, we take v to be log of u, and log of u is nothing but x cube plus y cube whole divided by x square plus y square, right? And what else we do, we know that now if we take v of lambda x lambda y, this is lambda cube of x cube plus y cube whole divided by lambda square of x square plus y square. So this is lambda times our function vx y only. So this is again a function of homogeneous of degree 1. And for homogeneous degree 1, we know that by Euler theorem, this function can be directly evaluated. So then v is of homogeneous of degree 1. Then what we can say, this value, this x del x by Euler's theorem, we have x times del u by del x, y times del u by del y, and this is by Euler's theorem. We know that this is n times our function only, and here the degree is 1, and the function given is x. So this is actually v, and this is del v, n times the function here we have here is v actually. So this is x cube plus y cube whole divided by x square y square. But we know that v is log u. So from this, what we can get, we get that del v by del x is 1 by u So this is 1 times u only. Now the thing is, this is v only. So this is 1 by u by del x, and del v by del y is nothing but 1 by again u times del u by del y. Then x del u by del x plus y times del u by del y. This would be nothing but u times x del v by del y, sorry, del v by del x plus y times del v by del y. Oh, actually we did something wrong here. We have to take v to be exponential of u. That's why we have a cancellation there. So there's one mistake there. So basically we have v equal to e raised to power u, and then this will imply that del v by del x would be eu del u by del x, and then del v by del y is eu del u by del y. Thus what we can say, we have x del u by del x plus y del u by del y. So the value of this is given by e raised to power minus u of x times del v by del x, y times del v by del y, and this we evaluate. This turns out to be e minus u times v only, and v, what was v? V is nothing but e times u, so this will give 1 only. So this expression, this will have value equal to 1 only. So basically the function given here was not homogeneous, but with the substitution, what we got, the substitution given as v equal to exponential of u, we got the new function to be homogeneous. And since the new function is homogeneous, we use the homogeneity of the new function, and then applying the Euler's theorem, we get the value of this expression directly without evaluating it. Okay. Okay, so moving on, and now let us have some more questions on how basically we use a second order partial derivative test, second order derivative test. So let's start. So the question is, which of the following is a critical point for the function? The function is given as x cube minus y cube minus 2xy plus 6, and the points are 0, 2 by 3, and then another point is 2 by 3, 0, and then another point is minus 2 by 3, 2 by 3, and the final point is minus 2 by 3, 0. So we have these 4 points and we have to check which of the following is a critical point. So for a critical point, what do we have to do? Either we have to plug in the partial derivatives to be equal to 0, or we have either of the partial derivative does not exist. So being a polynomial in a higher degree, this doesn't looks like the case that the partial derivative doesn't exist, because it will always exist. So to have the critical point, we just have to have the point satisfy the partial derivatives to be 0. So let us calculate the partial derivatives. So fx would be 3x square minus 2y. Fy would be minus 3y square minus 2x. So what do we want for critical points? I have this. Since these partial derivative exists, so we have the question of finding the critical point boils down to finding just the values of fx, fy equal to 0, 0, the points at which my partial derivatives are 0. So for critical point, we need fx and fy both equal to 0. So since we need both of these values to be 0, 0, so let us write the values fx at we have 3x square minus 2y be equal to 0, and then we have minus 3y square minus 2x equal to 0. So what this is implied? This implies that 3x square equal to 2y and 3y square equal to minus 2x. So we have y is equal to 3x square by 2. From the first equation, let's plug in the value of y in the second equation. So minus 2x equal to 3 of 3 by 2x square whole square. So what this gives? This gives x raised to the power of 4, 27 by 4x plus 2x equal to 0. And when I compute again, this will be x 27. So let us take 2x outside, is 27x by 8. And again, this can be written as twice of x. So basically this thing is 0 either if x to be 0, or this 27 by 8x cube plus 1 to be 0. And this is 0 if only if x cube is minus 8 by 27. And this implies x has to be minus 2 by 3. So this will imply what would be the value of y. If x is 0, this will imply y is given as 3x squared by 2, right? 3x squared by 2. So this is 0. So we have 0, 0 is a critical point. And then what do we have here? If I put my x value to be minus 2 by 3, this will imply y is 3 by 2 minus 2 by 3 square. So this would be 3 times 4, 2 times 9. So this would be nothing but 2 by 3. So this implies minus 2 by 3, and 2 by 3 is a critical point. So given the points, we see this is only option 3 is the critical point given in the option. So give the third option is the required critical point over a function. Okay, so I hope that's clear. So moving on. So let's have one more question. So likewise, as we calculated the Jacobian in 2 dimensions, what we can do, we can evaluate the Jacobian in higher dimensions as well. So let us evaluate a Jacobian in the 3 dimensions so that we have clarity how can we calculate these Jacobians in higher dimensions. So question number 9. So if my function u is given as x cube plus y cube, v given as, so u is also a function of x, y, and z. So let me write then v given as xy plus yz, and that's a w of is given as z minus x minus y. So now what do we have to do? Then we have to evaluate the value of then find the value of del u v w of del x y z at x points at point basically 1 1 1 1. So like the way we define Jacobian in 2 dimensions, same way we can define the Jacobian in higher dimensions. So this del u v w del of x y z, this would be determinant of a 3 cross 3 matrix. So this can be given as let me put u v w here, and then x y z. Then del u by del x. This was here we have del u by del x. Here we have del u by del y. Then we have del u by del z, because we are in the denominator we have del of x y z, so we have to differentiate with respect to x, y, and z. Del v by del x, del v by del y, del v by del z, del w by del x, del w by del y, del w by del z. So we have to evaluate all these partial derivatives. So let us try and plug in the values, and we have to evaluate this value at 1, 1, 1. So my u is given as x cube plus y cube, and the point is 1, 1, 1. So del u by del x is 3x square. So at the point it would be 3 only. Then del u by del y would be 3y square. So this would be del u by del y at point P. I am defining point P is 1, 1, 1 only. So del u by del y is again 3. And then if I evaluate del u by del z, this is 0. So at the point it will also take the value 0 only. Similarly, we have v given as xy plus yz. So del v by del x is y only. Del v by del y would be x plus z, and del v by del z is nothing but y. So at the points, these value will be 1. This is 2. And this is 1. And finally, we have w given as z minus x minus y. So del w by del x would be minus 1. Del w by del y would be minus 1. And finally, del w by del z would be 1. So let us plug in these values in this thing. So del of u v w or divided by del of x, y, z. So the values we have here 330. And then for v, we have 1, 2, 1. And this is minus 1, minus 1, 1. So you have to evaluate this determinant now. So this would be, we can evaluate with the help of just expansion. We know how to evaluate the determinant of a 3 cross 3 matrix. So this is 3 times 2 minus minus 1 minus 3 times 1 minus minus 1. So this would be 9 minus 6, which actually comes out to 3 only. So the value of this Jacobian is 3. So this is nothing but just we have to compute the things, and finally after computing we can just evaluate the Jacobians. And I hope the idea is clear. We have to just you just use these u v w, these things that keep in mind, and after that you can write the value of the Jacobian and any Jacobian, because after it's just a computation. Okay, so let's wrap our session with the one final question. Let's find a line in the last at the ending of the sessions. What we did, we found the maximum, or basically the absolute maximum and absolute minimum value of the functions. So let's have one question based on that. So let's have a final question, which is based on the finding the basically the maximum value or absolute maximum value of function on a given domain. So the question we have here is, find the maximum value of the function fxy given as xy on the line segment x equal to t, y equal to t plus 1, where my t is varying from -1 to 0 is. So if you see, so this is my x and this is my y. So when I take my t equal to -1, my x would be, the point would be -2 0, and for t equal to 0. So this is a straight line, as you can see. Basically x and y would be 0, 1. So if you have this -2, so this is the basically the line on which I want to evaluate the want to see the maximum value of a function. Okay, so how do we do that? This can be just we can apply the chain rule. So I know that my function is given as df by dt this would be by chain rule del f by del x dx by dt plus del f by del y dy by dt. So this is coming from the chain rule. So when I put the values, so this would be del f by del x would be, my function is xy, so del f by del x would be y, del x by del t would be 2, del f by del y would be x, and del y by del t would be 1 only. So this is 2y plus x, but I have to put my function in t in terms of t only. So this would be 2 times what is y? Y is t plus 1. So 2 plus t plus 1, and x would be 2t. So this is 4t plus 2. So now this is my f. So if I can write this as f dash t. So for a one variable function, so have the maximum, it happens at the critical point or the or at the boundary extreme points. So to find the critical points, I just put the value f dash t to be 0. This implies 4t plus 2 equal to 0. And this implies that my t is nothing but -half. So possible values which I have to check the maxima and minima is t equal to 0, t equal to -1. These are my boundary points, and t equal to -half. So let me check the values of my function t, then function is fx5, but this is nothing but given as what? This is given as 2t times t plus 1, right? 2t times t plus 1. So either we're checking 0, -1, and then minus half. So at t equal to 0, this will be 0. This will again be 0. This will be 2 times minus half, and then this is plus half. So this is minus half only. So as we can see, these are 3 points at which we have to see, and we can see this is these points are basically the points which I'm getting the absolute minima, or this is my absolute minimum, and this is my absolute maximum, my bad, absolute maximum, and this is my absolute minimum. And these are the points, basically these are the points at which my minima and maxima occurred. Okay, I hope this is clear, and with that we see that how we can find the value of absolute maximum and absolute minima when we have a basically a domain which is given to be parameterized by some another variable. So it's the same as just finding the critical point, so that we get all the points where the local maximum and minima is given, and then we basically what we do, we evaluate the function at these critical points and also at the boundary points, and we see basically, and then we see explicitly which values we are getting the absolute maximum and absolute minimum. So that's how we basically calculate the absolute maximum minima of a function. Okay, and with that, I guess I'd like to end my session here. Thank you.